So for our radiations second lesson, for radiations, the second lesson, I would like us to review what we learned in our previous lesson, whereby we noted that when a radioactive substance undergoes decay or radioactive decay, there are some radiations that are emitted. And among the radiations, we have the alpha, beta, and gamma. So in my previous clip, I explained how you can classify the radiations as either alpha, beta, or gamma. So if you've not watched the lesson 1 for radioactivity, kindly find it on this channel. So the types of radiation that we talked about, we said that alpha radiation are positively charged and they have a relatively higher mass, and thus they're the least deviated. So because the alpha radiations are positively charged, then we expect that they'll be deflected when they're subjected to either an electric or a magnetic field. Same to beta particles. When beta particles are subjected to any of the fields, we expect that the beta particles will also be deflected. So the direction in which the particles will be deflected depends on the charge. So basically, I want us to look at the two diagrams that I've given to you. So there is a diagram on the electric field, and there is a diagram on the magnetic field. So I want to explain something on the electric field. Within, for the electric field, we have a radioactive substance that is placed within a lead block. So this radioactive substance that is placed within the lead block, when it undergoes radioactive decay, the radiations that are emitted. So for instance, if we take it that the radiation that are emitted are three, there is the alpha, beta, and the gamma rays, then the radiations will come out being in a straight line at the start. But when they reach this particular position where we have the electric field, with the upper plate being positively charged and the lower plate being negatively charged, then their behavior will change. The gamma rays will move through, not being deflected. Why? Because they don't carry any charge. Then the alpha particles, because they are positively charged, they'll be deflected towards the negative plate. The beta particles, because they are negatively charged, they'll be deflected towards the positive plate. And something else that is of importance to note, look at the extent of the deflection. The alpha particles are the least deflected, but the beta particles are deflected greatly. Why does that happen? It happens so because from the previous clip, we noted that the alpha particles have a mass of 4, such that they are heavier than what? The beta particles that has a mass 0, or a mass that is almost negligible. So because the beta particles have a relatively lower mass, they'll be deflected more, and the alpha particles will be deflected less. Then, how will the particles behave within a magnetic field? How will the particles behave within a magnetic field? So within the magnetic field, of course, beta and alpha will undergo a deflection, but gamma will remain being straight. Why? Because gamma is not charged. But beta will be the most deflected again, and alpha will not be deflected so much as beta. So at times, when you are provided with the three radiations, it becomes very easy for you to be able to identify which radiation is alpha, which radiation is alpha, which one is beta. But the moment you are given one, then the extent of radiation might not help us very much in identifying the radiation. So apart from us looking at the extent of the deflection, the other very important thing that you need to know is the direction of the deflection. And as such, then there is additional information that you need to know about these deflections. And for us to be able to, again, know the direction of deflection, we can also use Fleming's left-hand rule. And what does Fleming's left-hand rule state? Fleming's left-hand rule states that when the thumb and the first two fingers of the left hand are held mutually at right angles, with the first finger pointing in the direction of the field, the second finger pointing in the direction of the electric field, then the thumb will point in the direction of motion or the direction of force. So how do we use the same when we are trying to look at the direction of deflection? So for this, we are going to use our left hand, and you place the fingers of your left hand, that is the thumb, and the first two fingers mutually at right angles. So we said that the first finger, this is the finger that is just next to the thumb, represents the direction of the magnetic field. So looking at the diagram that I've provided for you here, the magnetic field is across. So if it is across, what does it imply? It implies that the field is down or the field is into. So basically, because today I'm using a laptop for I to be able to teach this, then the magnetic field is into the gadget, or rather into the laptop. So you are supposed to point your first finger, that is the finger that is just next to the thumb, should point into the laptop. And then, if we want to know the radiation that is deflected to the right, this one here, your finger should be placed such that the first finger points into the laptop, the thumb points to the right. The thumb should point to the right. And if you've done that rightly, you notice the second finger, the one that is supposed to point in the direction of current, is pointing downwards. So the finger that is supposed to represent the direction of current, if you compare the direction in which this finger is pointing and the direction of the radiation, the two are actually what? Opposite to each other. The two are actually opposite to each other. And from our Form 1 work on cells and simple circuits, there are charges that are negatively charged that are normally in the opposite direction to the direction of flow of current. So because our radiation is upwards, or rather the radiation is emitted upwards, and our second finger is pointing downwards, then definitely the radiation that is deflected to the right is beta. We can still do the same demonstration to find out the radiation that is deflected to the right. Not right, but left, because you are through with the one for the right. So you are supposed to place the fingers, of course, the fingers of your left hand mutually at right angles again. Then your first finger should point into the laptop. Then the thumb should point towards the left. So this time round, if you are doing the demonstration rightly, then your finger should be pointing. Your hand should be facing upwards. So the first finger, while the first finger is pointing into the laptop, the thumb should be pointing to the left. And then you realize that the finger that is representing the current, the direction of flow of current is pointing upwards. So the finger representing the direction of flow of current is pointing upwards. That is the same direction in which the radiation is being emitted. And when such happens, then the radiation that is being deflected to the left is the alpha particle, or rather the alpha radiation. You can pause and replay, try to find out whether you are able to memorize that. Then, if it is a bit difficult, of course, you can make a comment, then I'll do more demonstration. So we move on to another slide. There is a slide that is representing the penetration power of radiations. We've talked about the 3 radiations. We've said that because these radiations possess different amounts of energy, then their penetration will actually be different. So from the diagram presented there, we have the alpha particles. The alpha particles have the least penetration power to an extent that they can be stopped by a piece of paper. The beta particles can pass through a piece of paper, pass through the human body, and they can be blocked by the thin aluminium. Then the gamma rays. Gamma rays can penetrate through a piece of paper, through a person's body, through a thin aluminium, and then they'll be stopped by a thick lead. And the gamma rays, the penetration power is almost like the one for what? The X-rays. We will be able to compare the difference between what? The gamma rays and the X-rays in our other lesson. Then the summary of properties. The properties that I've talked about can be summarized in a table like the one that I have. The alpha particle is a stream of just helium nuclei. I explained that in the first lesson on radioactivity. It has a positive charge. Its relative mass is 4 units. The velocity is very low compared to the other particles. It can be absorbed by a thin paper. The ionization power is strong, or rather it has the highest ionization power, and it is slightly deflected. And I've also explained why it is slightly deflected. And then the beta particles, this is a stream of electrons that have a negative charge, of course. The mass is almost negligible. The velocity at which they move is relatively higher than that one of the alpha particles, but less than the one for gamma rays. It can be absorbed by an aluminium plate. Ionization power weak, and they are greatly deflected. Then the gamma rays, these are just electromagnetic radiations. They have no charge. The relative mass is negligible. They travel at the velocity of light. They can be stopped by a thick block of lead. And then the ionization power, the weakest. And then they are not deflected. And of course, I've already talked about the deflection. Thank you very much. We meet again for another lesson. That is our 3rd lesson. Kindly remember to like the video. Also remember to subscribe so that you will be notified anytime there is a new lesson being uploaded. Thank you. Thank you very much.